Today we're going to do a classic lab where we burn magnesium in the presence of air so that it will combine with oxygen to form magnesium oxide. By taking very good measurements before and after the reaction, we'll be able to figure out what is the composition of magnesium oxide, and we'll be able to work out the chemical formula for magnesium oxide at the very end. The first thing I have here in the balance is a dry and empty crucible. It is 25.1097 grams. Right here I have a piece of magnesium ribbon. I'm not expecting great results from this lab because my magnesium ribbon is pretty old and it's likely already got some oxidation on the outside. I hit it with some sandpaper, but I think I was not able to get all of the oxidation off. So with the crucible and the magnesium, we are at 25.1358 grams. Now it's time to get it over to the ring stand and get burning. Okay, I've set my crucible up in a clay triangle on the ring stand above my burner, pretty close because I want to try to heat it as quickly as possible. And for the beginning, I'm going to heat it with the crucible lid on because this could take a while. We have to get up to 470 something degrees Celsius before the magnesium will auto-ignite in the presence of oxygen. And depending on the output of your burner and depending on how well insulated your crucible is, this could take as much as 10 or 15 minutes or more. If your magnesium ribbon is extremely oxidized, it may never start burning at all because the outer layer already is covered with the magnesium oxide and it won't allow oxygen to get to the bare magnesium. As we heat this, I'm going to lift up the lid about every minute just to check and see if the burning process has begun. So after I ran out of gas, I refilled the burner, reheated the crucible, and it finally did burn after about 15 minutes on the heat. It's cooled down enough now so that I can touch it. And there we have the burnt magnesium oxide. Unfortunately, it also has a tendency to react with the nitrogen and other compounds in the air. So we need to do another reaction, and that involves putting a little bit of water in there and then heating it up to evaporate the water away. Okay, I'm going to drip in a little bit of distilled water, and that should take care of any nitrogen-based side products that we got in this reaction and leave us with just magnesium oxide. I'm going to use a bit more water than I need because it should be able to easily steam off. I'll leave the lid just slightly ajar to allow the steam to come out. And once this finishes heating, we'll let it cool and find the new mass of our magnesium oxide compound. And the crucible has finally cooled down to a point where I can touch it, So I'm going to move it over onto the analytical balance, and we will see what our new mass is. $25.1557 grams. Here's how we do the calculations for the magnesium oxide lab. We started with the dry empty crucible at 25.1097 grams. And then after we added the magnesium ribbon into it, we had 25.1358 grams total. The difference between those two numbers is the mass of magnesium that we started our reaction with, which is 0.0261 grams of magnesium. After the reaction in which the magnesium burned, we had a total mass with the crucible included of 25.1554 grams. If we subtract the original mass from that mass, which is the 25.1358 grams, because that was the mass before the reaction, to be subtracted from the 25.1554 grams, the mass after the reaction, well, that's the difference that was caused by adding oxygen. And that difference is 0.0196 grams. Now that we have the mass of our two elements, we can work out the mole ratio between those two elements. And in order to find the mole ratio, the first thing we have to do is convert the grams into moles. So we take 0.0261 grams of magnesium and we divide it by the molar mass of magnesium, which is 24.305 grams. And that gives us 0.001074 moles of magnesium. We do the same thing with oxygen. We had 0.0196 grams of oxygen. We divide that by the molar mass of oxygen, which is 15.999 grams, and that gives us 0.001225 moles of oxygen. Now we need to consider the quantity of each element in moles. Now these numbers are pretty similar, 0.00107 versus 0.00122, and if you're going to be really particular about the ratio between them, it turns out to be 57 to 50. But that's an unreasonable formula for us to have for magnesium oxide. We wouldn't have 57 magnesiums and 50 oxygens. So if you divide both by the smallest number, we get a 1 to 1.14 ratio. And I'm satisfied that within the experimental error that's possible, that's approximately equal to 1 to 1. So I'm going to go ahead and say that the formula is likely to be MgO for magnesium oxide. And we can confirm that with our knowledge of ionic compounds. We know that magnesium should form an ion with a positive 2 charge, and oxygen should form an ion with a negative 2 charge. And a positive 2 and a negative 2 need only one of each ion to balance out to a net charge of 0.